Hello, gang! In a previous video, I tried to control a stepper motor directly using 4 GPIO pins of a USB-based interface and manually iterating through the stepping sequence. It worked okay, but the biggest limitation was of course the update frequency. If I were to drive a motor using half stepping at maximum speed of let's say 1000 RPM, I would need over 5000 updates per second, which isn't possible with this setup. So what I want to do instead is move the high frequency stuff to a microcontroller and talk to it via some sort of command-based protocol. Such commands could be start, stop, set speed, change direction, and so on, and the controller does the rest. There are a number of established industry standards for the communication between microcontrollers, and from what I see on the internet, I2C seems to be quite versatile and popular. With the popularity comes several freeware C++ libraries that can be used on Windows and even on a microcontroller architecture. However, after looking at some code snippets here and there, all of those libraries appear to have blocking read and write calls, which I want to avoid. I may be wrong, of course, but responsible research has never been my strong side, so I'm going to make my own. Before we begin, let me bore you with some theory. I2C, or I2C, or TWI, is a two-wire bus protocol. Bus meaning there can be multiple nodes sharing the same two wires. A node could be anything, a microcontroller, a sensor, software on a PC. Hell, if you want, you can Morse in the data by shorting two pins with a screwdriver. Yeah, that's right. I'll do that later. One thing to keep in mind is that both wires are always connected to 5 volts, which represents logic high. If any node on the bus wants to signal logic low, all it's got to do is connect the wire to ground. Each line has a particular job. The clock line isn't very spectacular. It carries the clock signal, which is basically a rectangular wave ticking along at some frequency. The data line carries information which is sent by some node and received by another. The clock helps the nodes to stay in sync. Each node is assigned one of two roles, master or slave. On a bus, there is one master and multiple slaves. The master has exclusive control over the clock line. The slaves may read the clock signal, but they must not change its value. Write access to the data line is switched between master and slaves depending on whose turn it is. When nothing is going on, the only output is the clock signal. In fact, even that might be disabled because a clock signal is only needed during active communication. The clock signal has two parts. The first half is low and not so important. The second half is high, and that is when the receiver evaluates the data line. Now here's the important part. There are 4 ways for data to go through the bus while the clock is high. Staying high all the way, staying low, falling while the clock is high, that is also called the start condition, or rising while the clock is high, also known as the stop condition. The first 2 conditions are used for data transmission, the second 2 for communication control. Let's look at a practical example. 1 master, 3 slaves, nothing is going on. The clock is ticking, the slaves are on standby, monitoring both data lines. When the master wants to talk, it pulls the data line low with the right timing to produce the start condition. The slaves recognize the pattern, wake up and get ready to receive further data. Now the master has to declare which slave device it wants to talk to. That is done by sending an address sequence of usually 7 bits. The slaves receive the address and compare it against their own. If one of the slaves recognizes its own address, it responds with a low signal cycle called the acknowledge. The other slaves go back to sleep. At this point, master and slave can communicate exclusively until the master sends the stop condition. From there on, the details are more or less application specific. Let me outline some of the design choices. As indicated earlier, the whole communication can be decomposed into individual cycles. Each cycle is going to get a resolution of 8 bits, and each bit is going to determine whether or not the line is grounded. Each cycle interval will span from mid-low to the next mid-low of 2 clock periods. That way, the data transitions are as far away from clock high as possible. In theory, this should reduce the risk of falsely identifying a data line transition as a start or stop condition. I know that in some implementations, the transitions occur at the falling edge of the clock cycle, and even though that isn't against the specifications, I don't know, it just doesn't feel right. So basically what's going to happen is that for every possible clock or data line pattern, I'm going to define a bit mask. To compose a message, I select the cycles that I need, depending on the datasheet of the device I want to talk to, stitch them together, and iterate through the message at an 8-bit per cycle resolution. In each frame of the program, the signals are then forwarded to the GPIO pins. The plan is to operate multiple master and/or slave nodes on the same platform simultaneously. Okay, let's look at some of the code. What I have so far here is more or less tested, at least in a closed console environment. I'm going to make it available at some point, at least when requested, and then you can download the code. And when you do that, you're going to realize that it's not very well documented. And by not very well, I mean not at all. So consider this walkthrough the documentation. The first thing we have is a couple of global type defs and enumerations that I'm going to use for various purposes. A signal enumeration, low, high. Then we have the cycle, and that one serves two purposes. One is as a symbol, like normal, and then the actual byte value is going to represent the time when the data line is pulled low. So for example, if you look at the low signal, you can read FF, and that means that the line is going to be pulled down all the time. Remember that each cycle has a resolution of 8-bit. Then I got a stream out operator for the cycle, so I don't have to decipher the bytes when I output them to a console. So this simply maps to some character arrays. Then there is the edge enumeration, and that one is going to tell me if there is an edge detected, either rising or falling, or if nothing's going on, if the signal is still low or high. Moving on to the second header, there are two more helper classes, the sequencer and the pulldown. The sequencer is probably conceptually the backbone of the whole thing, and the way it works is, first thing you do is you load it with a bunch of cycles. Count is going to let the class know how long the array is. That gives you the number of samples. So this is just the number of cycles times 8, because every cycle has a resolution of 8-bit. Then we have two sampling functions. One is get cycle at time, and that one's simply going to return the cycle at a particular time. So for the times 0 to 7, including 7, it's going to output the first cycle, and then from 8 to 15 it's going to output the second cycle. But that's not so important. The more important function is get signal, and that one is going to convert, well, not convert, it's going to sample the cycle at the specified time and return the signal value, so either high or low. And by time, it's not really a time, it's simply the sample offset from the beginning of the cycle sequence. So in a way, depending on your frequency, you can look at it at time, but it's basically a sampling index. Now the pulldown class is, as the name suggests, an interface to the data lines and clock lines, because the way I have designed the framework is that I don't have, or I did not want to have, access to the actual GPIO pins or the C functions that control the GPIO pins. So instead of controlling them directly, I'm going to use a simple integer or a pointer to an integer, and different nodes on the bus are going to have the same pointer. So whoever wants to pull down the line associated with the integer is going to increment the value by 1. And if you release the line, it's going to decrement. So essentially, it is a reference counted signal monitor. And you have the option to either set the signal or check the current signal. The MasterWriter class is similar to the sequencer with two differences. First, it handles two lines at the same time, the clock and the data line. And the second difference is it has some internal timing. Not exactly timing, it's more like internal stepping. So, like the sequencer, you can load it when in this case the function is called write, with a bunch of cycles. And once the MasterWriter is loaded, you keep calling the update function. Every time you call the update function, it's going to increment the internal counters, clock sample index and data sample index. Those are going to be fed to the sequencers for clock and data. The sequencers are going to output some signal, and that signal is going to be fed to the pull-down variables that are associated with the pointers that were passed at the constructor call. Now, when both counters have reached the maximum sample size, and they're going to do that at the same time because they're synchronized, the function isBusy is going to return false. So that's the point when the next message can be loaded for either writing or reading. Speaking of reading, let's take a look at the last header. The first class we have here is the line reader. That's a simple one. It's just going to remember the previous signal that was passed with the update function, and if there is a change with regard to the previous one, it's going to output the appropriate edge. So, rising edge, falling edge, or still high, still low. Then there is the reader. That one is a little more complicated because that's where the cycle matching happens. So every time update is called, it's going to send the clock and data signals to the line readers. The line readers are going to try to detect the edges, and then depending on the timing, it's going to try to convert that into a cycle. Most of the time, the value for the cycle is going to be incomplete because it takes 8 samples to reconstruct a complete cycle. But other than that, it should return one of the valid ones. And if none of that happens, that probably means that something went wrong. The master reader works similarly to the MasterWriter, except it's in reverse. So you load it with a cycle sequence, except this one is used as output. And every time the update function is called, the class is going to look up the current signals at the clock and data lines, send those to the reader member, and that one is going to convert that into a cycle if a cycle is complete and valid, and if it is, it's going to be stored in the array. And again, when the stepping has reached the end, it's simply going to shut down. isBusy is going to return false, so that the caller knows that the expected number of cycles has been read. The first thing I want to test is the MasterWriter class. I'll do that by outputting some cycles. The sequence that I hard-coded internally will start with a start condition, followed by some 7-bit address, write flag, and a stop condition. That will use all the cycle types at least once, and I can check the sequence manually later. Doing this is a little tricky since I don't have an oscilloscope at the moment. So instead I'll capture the signal in the software right before I'd normally send it out to the pins and print its value to this UI component. I'd send the clock signal to the top one and the data line to the bottom. So this is the test user interface with the 2 signal monitors. Right now they're not connected to anything in the real world, no GPIOs or anything. They simply output whatever value is on the integer pull-down reference counter things. And it would have been clever to have a stop button. I'm gonna have to do this with a good old print button. Okay. Yeah, there we go. Okay. So what we should see is a start condition followed by 8 bits of data, in particular 1, 0, 1, 0, and 4 zeros, finished by a stop condition. Now let's see. So the first one, the first falling edge, is happening while the clock is high, so this seems to be a valid start condition. Then we have 8 data cycles with a constant data line during the clock high cycles. And the last signal is a rising edge, again, while the clock is high, so that seems to be a valid stop condition. Now remember that this has nothing to do with I2C really, because it's violating every protocol. Normally this would be 7 bits of address followed by a read-write flag, followed by an acknowledge flag, followed by more data, and so on and so on, and then somewhere the stop condition at the end. But this is just, like I said, to test the output of the different cycles, and it seems to be working okay so far. To test the MasterWriter's cycle matching feature, I've modified the backend to constantly read high cycles as if it was reading an infinite number of bytes. The data line pulldown is attached to this GPIO pin, so I can take the role of a slave with a screwdriver. As usual, the MasterWriter will try to match incoming cycles, which will be printed to the console. So the UI that I'm going to use for this test is almost identical to the previous one, except that it doesn't just cycle once through a sequence when I press the button. It's gonna switch to reading mode and stay there until I close the program. The clock and data lines are connected to pins 0 and 1 on the board, and all the other pins are pulled low. So when I make a connection with a screwdriver between pin 1, which is the data line, and one of the other pins, it's going to pull the voltage low. And hopefully the software is going to detect that as a low signal, and depending on the timing with regard to the clock signal, it should detect the 4 types of cycles that I have implemented. And that's pretty much what I'm going to try to do. As you can see, the frequency is slowed down to about 1 Hertz, so at least I got a chance to do something. Now for the high signal, I don't really need to do anything because the data line is high by default. So if you look at the console, you can read that it keeps detecting high cycles at the end of every clock cycle. To emulate a start condition, I have to make sure that the data line signal is high when it enters clock high, and then pull down somewhere in the middle. The low signal is trivial as well. All I gotta do is leave the pin grounded all the time. And for the stop condition, I have to leave the data line grounded and then release somewhere within clock high. To communicate with an actual device, we're going to have to take a look at the datasheet to find out what sort of messages it understands. For this test, I will use the X24C16 EEPROM, which has 2048 bytes of memory. The commands I want to implement are write byte and read random byte. The datasheet specifies the write command like this. The first byte is the start condition, followed by a 4-bit device address which is hardwired to 1010. I know that most sources claim that a device address must always have 7 or 8 or 10 bits, but here we are, this one only has 4. The next 3 bits are the bank address. The 2048 bytes of memory are divided into 8 banks, 256 bytes each. These 3 bits pick the bank. After that comes the read or write flag, low for write, high for read. After that, the master releases the data line and waits for an acknowledge, which technically is a low cycle. If the acknowledge is detected, the EEPROM recognizes its address and the master can proceed with the 8-bit word address within the previously selected bank. So effectively 10 bits, which I call the storage address, determine where the byte is going to sit. Once again, the master waits for the arrival of an acknowledge and continues by sending 8 bits of data. The slave sends a final acknowledge and the master concludes the transmission by sending a stop condition. The command can be implemented trivially by simply loading MasterWriter with the corresponding sequences and checking the output of MasterReader for valid acknowledge bits. Reading from the EEPROM is a little tricky because the read command doesn't provide means to explicitly specify the full storage address. Internally, the device has a variable that points to the location last accessed by either write or read operation. So the procedure is to start a write operation, which sets the internal memory pointer, but instead of writing data, the operation is interrupted and another start condition is sent, this time followed by the read operation. This is a little confusing because the 4 bits of the device address 1010 are still followed by the bank address. Only the word address is recycled from the previous write call. I suppose I'll have to investigate this at some point. After hours of tweaking and tuning, I can proudly announce that the current read-write top speed hovers at breathtaking 1 byte per second. I spent over an hour on writing a 32 by 64 pixel monochrome image to the device. After that, I ran out of patience, so in order to document the functionality of the read command, I'll just read a few random pixels instead of the whole thing, this time in real time. The I/O Warrior 40 that I'm using for this actually has a built-in I2C interface. It's still painfully slow due to USB, but at least it's bringing 750 bytes per second to the table. I'm going to give it a go sooner or later, but that's a topic for another video. Come on, buddy. Hang in there. Come on, come on, come on. Almost done. What? Oh no. Oh no.